Okay, I think that should be recording now. Okay, so welcome everyone. We're very happy to have Nicolas Boulle here this week. So Nicolas did his PhD in Oxford. He's currently in Cambridge doing a postdoc, and he will very soon be joining Imperial as an assistant professor. And he's here to talk to us today about elliptic PDE learning is provably data efficient. So thank you very much, Nicolas. And yeah, it's over to you.
Yeah, great. So thanks a lot for the invitation. So yeah, I'm going to talk about PDE learning, and so this talk will be based on a joint work with my collaborators, Diana Likas and Alex Johnson from Cornell University. So I'm working in the broad area of scientific machine learning, which is a relatively new area at the intersection of numerical analysis and machine learning, where researchers are trying to essentially combine classical techniques that have been developed in the past 30 years in numerical analysis for solving partial differential equations or discretizing functions, discretizing PDEs, and together with combining these techniques with data and with modern machine learning techniques like deep learning and neural networks. And so the aim is to combine these two areas and to essentially make scientific discoveries, so to discover physical laws, unknown physical laws from observational data. And so there have been quite a lot of recent successes and recent applications in the field of scientific machine learning. So the first one, which you may have heard of, is about weather forecasting. So there was a paper about a year ago from a team in DeepMind and another team in Caltech, where they apply machine learning techniques along with techniques from numerical analysis to predict weather. So they essentially combine knowledge of historical data from weather along with neural networks that approximate the next time forward step of the weather. So trying to predict the state of the weather in 1 hour or 6 hours. There have been also some work on the protein folding problems in biology, and as well as another team in DeepMind did some work on materials discovery. And something that is closer to my area, which is a recent paper by Resi Yazdani and Karniadakis, where they try to perform numerical simulations using this called physics-informed neural network framework to try to compute fluid flow inside a biological setting. So to try to compute the solution to the Navier-Stokes equations, having only knowledge of, for instance, boundary data. And so, in my opinion, there are essentially three distinct subfields of in scientific machine learning. So the first one is what are called PDE solvers. So it's an area where you might have little amount of data available, but on the other hand, lots of prior physics knowledge. And so typically in these settings, you might have knowledge of the partial differential equation that describes your physical phenomena, but without much data, and you try to essentially compute the underlying solution satisfied by your governing equations. And so this is an area where you try to essentially compute solutions to PDE. So it's typically where you will find techniques like physics-informed neural networks or PINs. Another important area is what's called PDE discovery. And so this kind of sits in between, where you have some amount of data available and some amount of physics knowledge. So you might have, for instance, knowledge of some terms in your partial differential equation that describe your experiments, your physical experiments. And you might want to discover the coefficients in front of these equations while having some data regarding a solution that you observe. And so in this case, this sits more in the inverse problem type of questions, where you try to discover coefficient field from observation data, where you have a good knowledge of your underlying partial differential equations. And here there have been quite a lot of research in to develop what's called the Cindy algorithms, so sparse algorithms based on sparse regression techniques that try to infer coefficient fields in partial differential equations. And so I'm working in the another area, so the later area, which is called operator learning. And so this is a relatively recent field, so like something like 5 years ago. It has been introduced like 5 years ago, where you have lots of data available about your systems, but you don't have any physics knowledge, or you have very little amount of physics knowledge. And in this case, you want to essentially discover the operator that will map a source term to your equation to the underlying solution satisfied by your equations. So here the aim is not to discover the equation describing your system, but the aim is to find the solution operator that maps, for instance, one time step of your solution to the next time step. So essentially try to learn your numerical solvers without having your underlying PDE. So you can't use any classical techniques here because you don't know what the partial differential equation is. And so if you are interested in learning more about this area, we have released a survey recently on a guide to operator learning. And so in this talk, so the aim will be to learn the solution operator to unknown linear partial differential equations of the form L of u equals f, where L is your favorite partial differential equation. So for instance, a Laplace equation, a Laplace operator. And we don't know what L is, and we don't try to discover L because that would be an inverse inverse problems. But we try to discover its inverse that maps the source terms f to the solution u. And so in this case, if you have a good mathematical framework in a way, the inverse operator is compact, so it's essentially much easier to discover than the underlying partial differential equation. And once you have once you have discovered this operator, you can apply it at new source terms to predict the solution, the underlying solution. And so the main contributions that I will be describing in this talk will be first a theoretical result that quantify how much training data of the form f and u are needed to approximate this inverse operator. And then a practical deep learning approach to learn Green's function. So if we restrict to specific partial differential specific class of PDEs. And the key ideas will be essentially based on classical numerical analysis techniques. So this is not really a numerical machine learning type of results, but more exploiting numerical analysis to analyze machine learning problems. So we use randomized numerical linear algebra, PDE theory results regarding the regularity of Green's functions, and then a neural network based on rational functions. And so what are the standard approaches of PDE learning? So as I said, we want to approximate the solution operator that maps a source terms f to a solution u. And so the setup is that you typically have a physics experiment, so you have a numerical solver. And you are free to choose whatever source terms f you want to excite your system. And then you can acquire data regarding the underlying solution satisfied by your governing equation that you don't know. And so from pairs f and u, from training pairs f and u, you want to compute a good approximation of the solution operator. And so what researchers do typically is that they train what's called a neural operator, which are infinite dimensional analogs of neural networks that takes into input functions and outputs functions. So they train these networks, these neural operators neural network on the set of training data. And then the idea is that while it's expensive to do this training step, afterwards, you can evaluate it at new source terms and essentially predict a solution. So this has several benefits. So first, if you don't know what your operator is, you don't have any other classical, there is no alternative that can achieve this task. And even if you know what your PDE is, you may be able to discover a reduced order model that might be faster to evaluate than standard numerical solver, which could be useful for downstream tasks like optimization, for instance. If you want to embed your problem into an optimization framework, like shape optimization in material sciences, for instance. And so there have been several approaches that have been proposed in the past few years. So the main ones are like the DeepNet, the Fourier neural operator, and the deep green techniques. And they essentially all perform the same techniques, and they essentially differ by the type of neural network architecture that they use. So the DeepNet technique is based on essentially a branch network and a truncation network, and this is kind of performing a low-rank decomposition of your solution operator. The Fourier neural operator is based on essentially convolution neural networks and the fast Fourier transform. So it's kind of an analog of a spectral methods, if you like. And the deep green approach is based on an autoencoder. And so there are like several challenges at the moment in the area. So the first one is the lack of theoretical results. So there have been quite a lot of work recently on approximation theory, getting approximation theory type of results. So essentially understand the approximation power of these neural operators. So if you have a certain solution operator in a certain mapping between certain class of functions, we might want to know how much parameters in the neural network do we need to discretize it efficiently. But there are other theoretical questions that are still left unanswered. So one type of result that we might be interested to get is to understand what type of training data should we use. So what's the distribution of the source terms that we should use to probe our system, and how much training data do we need to train these neural operators. Getting some performance guarantees, for instance, regarding the optimization setup, understanding which neural network architectures are better than others for different type of PDEs, and whether these approaches are robust towards noise perturbation, for instance. And the second main challenge is essentially the lack of regarding the interpretability of the model. So unlike classical machine learning questions like image classification, here we try to discover physics phenomena. And so it's really important to also get not only a good prediction, so a good accuracy when we train the network, but also be able to extract, for instance, some physical laws that are meaningful for people working in the area. So we might want to, for instance, understand what are the dominant modes of the systems. Are there some symmetries or conservation laws? Are there some singularities or shocks? And so these are questions, these are properties that are typically very difficult to extract because the neural operators, so the neural networks that we use to train, to approximate the solution operators are very complex objects. So it's very difficult to build this prior knowledge, for instance, or extract this knowledge from the neural network that have been trained. And so in this talk, we'll focus on an observation, which is that the PDE learning essentially is what we call data efficient. So in the sense that unlike unlike most machine learning tasks, which require a huge amount of training data to train the neural networks, this does not appear to be the case when we train them on PDE data, when we train neural networks on PDE data. So as an example here, I'm reporting an experiment that I've done on a very simple problem, like a two-dimensional Poisson equation problem, where on the x-axis, I increase the size of the training data set, so the number of source terms and associated solution. And on the y-axis, I report each point reports one training of a neural network. So I report the testing error after I train a neural network on this, the number of the amount of training data given by the x-axis. And so you essentially see two behavior in this diagram on the left. So first, a very fast exponential decay of the testing error with respect to the size of the training data set. And then the testing error flattens due to essentially discretization error and the difficulty in optimizing the neural networks. And so we are interested in understanding how much training data do we need to learn a given partial differential equation, and why do we get this exponential convergence at the beginning until we reach optimization levels. And so to do that, we are going to consider a simple class of partial differential equations to essentially get some theoretical understanding of why this is the case. So we are going to consider linear differential equations of the form L of u equals f with Dirichlet boundary conditions, such that we know that there exist Green's functions, so that the solution u can be expressed as an integral operator with respect to the source terms f. So for this partial differential equation L, there exists a Green kernel G, which has twice the dimension of the original equation, such that the solution operator can be written as u equals integral of G times f, and the G is unique and doesn't depend on f and u. So once you know G, you essentially know your solution operator, so you can predict the solution at new source term. And so as an example, if I show you the 1D Poisson equation, so of the form minus d squared u dx squared equals f. So this is a Green's function associated with it. So you notice that it's in 2 dimensions because the original equation is in 1 dimension. And there are some properties of the original PDE that we can read on the Green's function. So for instance, the fact that the Green's function is symmetric is related to the fact that the original equation is self-adjoint. And you can also read, for instance, boundary conditions on the sides of the Green's function, essentially. And similarly, if we look at the Helmholtz equation, so this is with periodic boundary conditions. So this is the associated Green's function on the right. So we can read the periodic boundary conditions on the Green's function, and the number of stripes along the diagonal that we observe is related to the Helmholtz frequency k. So we can read some interesting properties of the equation by looking at the Green's function. And so in this talk, we are going to consider Green's functions associated to elliptic partial differential equations, which essentially model diffusion type of phenomena in 3 dimensions in the form minus div of a of x grad u equals f, where a is an unknown coefficient field with a very low regularity condition. And so A is unknown, but we are not interested in discovering the coefficient field A from of this equation, because that would be like an inverse type of, that would be an inverse problem. We are interested in discovering or approximating the Green's function associated with this equation. So we are interested in approximating G that satisfies this, such that it satisfies this integral equation u equals integral of G times f. And so our main result states that there exists a randomized algorithm that can achieve exponential convergence for approximating this Green's function with respect to the amount of training data f and u available. And so this is a randomized algorithm because we use random source times f to probe our system, sampled from a Gaussian process. And so this bound that we get, this exponential convergence bound that we get, comes with a probability of success as well. And the probability of success that the bound is satisfies is exponentially high, and it converges exponentially to 1 as we increase the amount of training data. And so the exponential convergence here that we get, so that essentially characterize the class of elliptic partial differential equations. So what we are saying with this result is that if we have an elliptic PDEs, you should aim when you solve it, when you approximate its solution operator with a neural network, you should aim to discretize it or or design your neural network to achieve exponential convergence. So what we say is it's an existence type of result in the sense that it's possible to achieve exponential convergence when we try to learn solution operator associated with this class of PD. And the convergence rate that we get here matches the experiments that I've showed you earlier on the Poisson equation. So the experiments that we do in practice, in practical experiments with neural operators, we observe this fast convergence, and this is something that essentially was unknown. And so while this is an existence type of result, I'm going to show you exactly what the algorithm look like. So the proof that we have is really constructive, and we know exactly what the algorithm is. And so the proof will combine essentially core techniques in numerical analysis and generalize them to infinite dimensions. So we'll use randomized singular value decomposition, hierarchical matrices, and peeling. Also, this essentially provides kind of a framework for using numerical analysis techniques to analyze essentially convergence results or to analyze neural operators or operator learning practical algorithms. And so first we'll go through randomized numerical linear algebra. And so the idea is that we essentially need a scheme for computing an approximation of the green function. And to do that, we'll compute a low-rank approximation of the green function using what's called the randomized singular value decomposition. So if we look first at the finite dimensional setting, so if we have a matrix A, so black box matrix A, so if we have a matrix A, we can compute its singular value decomposition from the form U sigma V star, where U and V are orthonormal matrices, and sigma is a diagonal matrix containing the singular values of A. Then the Eckhart-Jung theorem tells us that the best rank approximation to A is achieved by truncating A to its case singular values. And the approximation error that you get is essentially given by the tail of the singular values of A. So this epsilon k factor here. And so there is a landmark result by Alcor, Martinson, and Chop from about 10 years ago that says that if you have a black box matrix A that you can only achieve from matrix vector, that you can only access through matrix vector product, so you are only able to sample A at input vectors F, you can essentially compute a low-rank approximation AK to A from about k plus 5 random input vectors. So essentially, you need a tiny amount of oversampling above the rank, the target rank that you try to achieve. And so this result by Alcor, Martinson, and Chop, so this is known as the randomized singular value decomposition algorithm. So it's an algorithm that is useful if you try, for instance, to compute approximation to tall and skinny matrices from matrix vector products. Comes with rigorous probability bounds that essentially states that the error that you make in this approximation is a tiny bit worse than the best rank approximation error. So it's a square root of k factor worse than this epsilon k factor, so given by the best rank approximation. So you essentially what this result says is that you can compute a near best rank K or low rank approximation to A from matrix vector products. And so while this is a simplified statement, the result in the paper comes with full probability bounds with any amount of oversampling you like. And so to show you an illustration of how it works in practice, so on the this is a result like a diagram that shows that as I increase my number of samples, so my number of random input vectors that I use, the relative errors decays very fast and is a tiny bit above the best approximation error that I can get that is given by the Eckhart-Jung theorem. Okay, so this is a very useful result that we will use later on to compute an approximation to the green function. But before we need to generalize it, because this result was essentially stated using standard Gaussian input vectors. So in the original paper, you could only sample the matrix A at random vectors from standard Gaussian distributions, which are essentially whose entries are essentially independent and not correlated. And so basically we want to generalize this result to infinite dimensions, such that instead of approximating a matrix or matrix vector product, we want to approximate an integral operator from convolution against random functions. And so to do that, we essentially need to generalize the randomized SVD result so that we can use correlated Gaussian vectors instead of standard Gaussian vectors. And so this is kind of one of our main results, which tells that essentially it gives the same type of error bounds as the standard randomized SVD, but it allows for correlated random input vectors, so sampled from a Gaussian process with essentially any covariance matrix. And so the bounds that we get are similar to the randomized SVD, except that we have this beta k over gamma k factor that essentially depends on the prior knowledge that you have about the right singular vectors of the matrix. So essentially, if you have prior knowledge of the matrix A that you want to approximate, you can enforce that in the covariance matrix that you use to sample your random vectors to essentially trigger those dominant singular values directions. And so this beta k over gamma k factor allows us to enforce prior knowledge on A on the covariance matrix. And in some cases, if you design your covariance matrix carefully by taking into account this prior knowledge that you might have, you can basically get lower error, about 40–50% lower errors than the randomized SVD compared to the best approximation error. So this could be useful in settings where you are not allowed to make you are not allowed sampling the matrix would be very expensive compared to the numerical in algebra costs. And so now that we have this generalization of the randomized SVD, we are going to extend it to infinite dimensions. So we are going to consider Hilbert-Schmidt operators, which are essentially bounded linear operators between Hilbert spaces with finite Hilbert-Schmidt norm. And these are essentially generalization of matrices in infinite dimensions. So the Hilbert-Schmidt norm of a matrix coincides with the Frobenius norm. And a typical example of Hilbert-Schmidt operators are integral operators with a kernel G. So integral operators of the form integral of G times F. And basically all the properties of matrices in finite dimensions extend naturally in this framework to Hilbert-Schmidt operators. So the Hilbert-Schmidt norm of the Hilbert-Schmidt operator coincides with the L2 norm of the integral kernel that we have. They also admit a singular value decomposition. And there is also an Eckart-Young-Mirsky theorem, which tells that truncating the SVD gives us the best Ranke approximation in the Hilbert-Schmidt norm. And so with this setup in place, we can now extend the randomized SVD from matrices to Hilbert-Schmidt operators. So instead of computing a low-rank approximation to a matrix A from matrix vector products with random vectors F, we are going to compute a low-rank approximation of Hilbert-Schmidt operators from convolutions with random functions sampled from Gaussian processes. And so in this case, what you do is you select first a covariance kernel, like the squared exponential kernel. And from that, you can sample random functions and use the same algorithm as the randomized SVD. And so the theorem that I stated earlier essentially extends in infinite dimensions to this setting, where we can use a tiny bit amount of oversampling to compute a Ranke approximation to the Hilbert-Schmidt operator, or to the underlying kernel associated with the integral operator. So we have a bound that states that the L2 error between G and its Ranke approximation is essentially a tiny bit worse than the best error that you can make, which is by truncating the singular value decomposition of G. And so if we do a simple application with this exact kernel that I give on the left, on the top left, the bottom left picture is the one that I learned or that I approximated with the randomized SVD. And so on the right, I'll report the relative error made by the randomized SVD with respect to the number of samples that I use. And so we have three different curves here. So the black curve is the best approximation error that you can achieve. And the other curves are basically achieved using different distribution for the random functions. So in those cases, I used a squared exponential kernel to sample the associated random functions that I used in the randomized SVD algorithm. And the length scale parameter gives us a different relative error. So this is basically understood by our bounds. So these are the gamma k over beta k factor. So depending on the length scale parameter that I use, I sample a higher dimensional space of random functions, and I'll be able to achieve lower relative error. So if I use a very small length scale parameter L in the covariance kernel, I can achieve a near best approximation error to the underlying kernel here. And so we now essentially have all the ingredients in place to compute an approximation to the Green's function. So we can apply our theorem directly to the Green's function of the elliptic PDEs. And we get these probability bounds here, which depend on this epsilon k factor. So that depends on the singular values of the underlying Green's function. And so to be done, we essentially need to understand how this epsilon k factor decays with k. And remember that here our aim is to show an exponential convergence of the Green's to the Green's function. So we want this epsilon k to decay very fast with k. So the issue that we have here is that the Green's function are not smooth near the diagonal. So if you look at, in particular in 3D, Green's function take even infinitely large values along the diagonal, so they're not bounded. And so essentially this implies that this epsilon k factor decays very slowly with k, so it decays algebraically with k. But we want to reach an exponential convergence. And so to do that, we're going to exploit other properties of Green's function, essentially its regularity properties. And so while Green's function are not smooth, so they are not low rank on the entire domain, what we know from a result by Bubendorf and Hackbusch in 2003 is that they are low rank on well-separated domains. So if you take the Green's function and you restrict it to a domain x cross y, which are well separated, so they're not connected to each other, like the blue and green domain in this picture, then the Green's function restricted to these domains is low rank, has a low rank structure. So its singular values decay very fast. But if the domains touch each other, so they are essentially connected, not separated, like the blue and red domains, then the Green's function, so these are domains located around the diagonal of the Green function. The Green's function is not low rank on these subdomains. And so this essentially this low rank type structure induce a structure of the Green's function, so hierarchical structure, so we can partition it hierarchically so that we discretize it as low rank substructures essentially. So the green domains here are domains where the Green's function is low rank, and the red domains along the diagonal are domains where the Green's function is not low rank. And so what we are doing now is that we look at each of the green structure here. So in this case, the Green's function is low rank, so we can approximate it well by a low rank function, which implies that it has fast singular values on these subdomains. And so we can essentially apply the randomized SVD on each of these subdomains. And so in this case, we use this in a hierarchical manner. So we use the randomized SVD in a hierarchical manner. So first, the bigger domains first at the first levels of the hierarchical partition, and then we go down the level and progressively refine our approximation along the diagonal in a way that we use a lot of matrix vector products that we do so that we don't use a high number of training data in this case. So this is called we employ what's called a pinning algorithm here. And so now that we have approximated the green function on most of the domains, so all the green domains where green function is low rank, we just need to deal with cases where along the diagonal. So we just need to approximate the green function on the red domains along the diagonal here. And so to do that, we're going to exploit another result from PDE theory, which is about the decay along the diagonal of Green's function. So while this Green's function is not globally smooth, it has a certain decay that we control and that we know from PDE theory along its diagonal. And so this is essentially due to a result from Grunter and Widman, which bounds the decay along the diagonal of the Green's function. And it tells us that if you look in the L2 norm along the diagonal, then the Green's function decays at a certain rate here. And so what we can do is that we can perform this Yarkov structure, and the Green's function, essentially the norm of the Green's function on these red domains is going to decay as we progress, as we refine it towards the diagonal. And so we can essentially do as many levels as we need until we can safely neglect the Green's function by approximating it with 0 along the diagonal and make an error epsilon. And so in this case, if you do that, then we can make error epsilon by using as many data as we need on the domains away from the diagonal with the randomized PDE, and then make error epsilon by neglecting the Green's function along the diagonal. And this essentially achieves the proof of this data efficient result that I showed you earlier. So as a summary of this result, we constructed a randomized algorithm that achieves exponential convergence for approximating the Green's function with high probability of success, which essentially combines both the randomized SVD and the Yarkov structure of Green's function. And so I want to highlight that this is more like an existence type of results, because in practice you wouldn't want to employ this specific algorithm because this might be difficult to perform this Yarkov partition or quite expensive. So in practice, people would prefer to use neural operators, which are simpler to implement in a way. But we see this result as a kind of a motivation for designing neural operator architectures in a way that it tells us which convergence ways should you expect when you design your neural operator, when you set up your neural operator technique. And also it also guides us towards what kind of training data, so what data distribution should you use to as training data for your neural operators. And so in the second part of this talk, I'm going to describe now a practical deep learning approach that aims to approximate Green's functions of PDEs from data. And before I do that, so I just want to highlight that this result, even though we stated it for elliptic PDEs, you can also extend it using similar techniques to time-dependent PDEs like heat-type equations, so parabolic PDEs of this form. So now we are going to look at deep learning applications. So we are going to design the deep learning methods for approximating the Green's function. And so essentially, we start first by selecting our covariance kernel. So we know it's if you can enforce some prior knowledge on the covariance kernel, you will achieve better approximation results once you have trained your neural operator. And then from the covariance kernel, we can essentially sample random source terms that we use to excite our system and observe the underlying solution. And once you collect source term and solution, you can then design your loss function in a way that captures the Green's function. So if you have a linear partial differential equation, our method essentially use a specific loss function that enforced this integral operator relationship, so that instead of approximating the integral operator directly, which is an object between infinite dimensional function spaces, we aim to approximate the Green's function, the Green kernel, by a neural network. So that takes only two inputs and outputs g of x, y, essentially. And the idea is that once you have trained your Green's function neural network, you can then extract and visualize the Green's function to get more physics information than alternative techniques, which are more general, but also more complex to analyze later. And so what kind of properties can we extract from Green's function? So once we have learned the Green's function and the homogeneous solution that captures the boundary conditions, we can also actually extract symmetries and conservation laws from the Green's function, which are related to the symmetries of the PDE, or perform an eigenvalue decomposition and understand the dominant eigenmodes and eigenvalues of the Green's function, as well as the singularity location in the PDE. And this is supported by the type of neural network that we use to approximate the Green's function. So we use rational neural networks, which are neural networks with rational activation functions. And so there are two benefits of using these neural networks. So first, we show that they have high approximation power, so higher approximation power than essentially ReLU neural networks. And secondly, we use rational functions, so they can take arbitrary large values, which is ideal for approximating Green's function. We can also take arbitrary large values along the diagonal. And so as an example, I'm going to show you a simple first advection diffusion equation where I'm on an interval -1, 1, where I'm turning on the advection term only on the right half of the domain. And so I'm generating then training data, training my Green's function neural network, and then visualizing it now. So on the left, we pose the Green's function that we recovered from this equation. So first, there are essentially two behavior that we can see. So first, on the bottom left part of the Green's function, we see a behavior that is typical from diffusion phenomena. So we can tell that our equation is diffusive, has a diffusive behavior on the left part of the domain. While on the right part of the domain, the Green's function that we recover is typical from an advection behavior where the information travels from left to right. In the middle, we plot the homogeneous solution. So we see a good agreement between the exact and the learned homogeneous solution. While on the right one, so I'm showing you a picture that is typical from using rational neural networks. So I'm evaluating by homogeneous rational neural networks on the complex planes, and I'm showing you the phase portrait of these rational neural networks. And we know from rational approximation theory that the poles of the rational functions, approximating my function, essentially cluster towards singularity of the underlying function that it approximates. And so we can see here by looking at the poles where the color changes rapidly, so these are poles of the rational functions, that the poles tend to cluster towards x equals 0, where there's essentially a change of physics in the equation. And so by analyzing the pole location and the speed of clustering of how the pole cluster towards singularities, we might be able to extract some information regarding shocks and singularity locations of partial differential equations. And as a final example, I just want to show you Stokes law in a lead-driven cavity. So this is a famous example from computational fluid dynamics, where we have fluid velocity traveling on the top of the lead from left to right. And I'm showing you the exact velocity magnitude here on the top left. So this corresponds to the homogeneous solution of the system. And on the bottom left, the one that we approximated by our Green's function neural network. And so we see essentially a very good approximation between the two, except at the corners, which is due to the relatively coarse maze that we use in our simulation. And on the right, I'm showing you an interesting figure, which is the Green's function that we recover associated with the Stokes equations. So in this case, we aim to map the x and y component of the body force terms F, so Fx and Fy, to the x and y component of the velocity u corresponding to this source times f. So these are the training data that we use to train our Green's function neural network. And so since we have two functions as input and two functions as output, there is now a matrix of Green's functions that will act on this x and y component of the source times f and return the x and y component of the velocity u. And so by analyzing this matrix of Green's functions, so essentially looking at the relationship between the terms in this matrix, so looking at the symmetries, we can understand some properties like the coupling type properties of the underlying equations. And so with that, I'll conclude my talk. So in this talk, we showed we described a theory for approximating Green's function that tells us convergence result of neural operators. This relies on a generalization of the randomized SVD to first correlated input vectors and infinite dimensional functions. And finally, we described a deep learning approach that is based on rational neural networks. And if you are interested, there's a TensorFlow package available online that you can install. And with that, I'll thank you for your attention. I'll be happy to take any question.
Okay, thank you very much, Nicolas. Yeah, I'll just stop the recording and then we can go to questions.